Can you believe it? We are at the end of the semester. So this is the last set of announcements for the semester. Most of them are familiar to you because this is basically the same announcement that we had before. There's a homework that's due today, and there's a final project that's due today. There's a final exam that happens day after tomorrow. The homework, of course, you get your one late day if you choose to use it in exchange for 10% of the points for the final project. Don't forget there are submissions both on Kaggle and on Canvas, and you'll have till the 30th to submit your report on Canvas with no penalty. I think for Kaggle, the deadline is the 27th. Someone can correct me if I'm wrong. I think it's the 27th, but don't push it to the last day. The final exam covers everything. Not everything. It covers everything that we did in the second half of the semester, plus all of learning theory. And it's for 2 hours, so it's a little longer than the midterm. And it's at 10:30 in the morning, not at the usual class time. So if you show up at the usual class time, that's when we'll be wrapping up. And my office hours today will be in MEB 3105. If you don't really want to remember that, you can just follow me, and we'll find our way there. Any questions? Yes.
Will you be able to comment on whether linear classifiers are relatively good or bad on the final project?
It depends on the data that you use.
Okay.
I can comment on this, and people have asked me about this. So it really depends on what features you're using. Different features show very different performance. So I've heard, I can tell you from my implementation. In my implementation, GloVe performed worse than the other features, which was kind of interesting because GloVe is supposed to be a neural network and all that. Well, not really a neural network, but anyway. And the biggest win I got came from using the miscellaneous data. That's the amount of information I'm willing to give.
Would it be more like the range, like if you use TF-IDF with SVM or LG, it's like I'm expecting somewhere of accuracy with this range?
Yep.
Would it be a bigger range or would it be more like a big 0.1 difference?
0.1 is too small. There'll be like 1% up or down. And I'll talk about this later today also, but I found that you train an SVM, you do the hyperparameter selection the right way, or you train logistic regression and you do hyperparameter selection the right way, your classifiers will be exceedingly similar to each other. Should be. Yeah.
For the submission on Canvas, we have to show the training, the cross-validation training.
For the report?
Yeah.
So the report, there's like a set of questions that you're answering. You don't need, you can share as much information as you want. Just keep it to 6 days.
Like for the project, we have to turn in our code, right?
Yes.
Do you want it where we have it where the code runs cross-validation?
No, actually, I prefer not because that can take forever. You know, when you run it, just bake in the best hyperparameters or read it from a config file or something. Yes.
Where should we submit the code?
On Canvas.
Oh,
So your Canvas, I think you'll need to submit both your code and your report.
and they'll be in separate files.
I hope, yes, yes. So many hands. I'll go from the back. Yes.
So how do you want us to submit? You want us to submit the pre-processing steps that we took?
I would prefer that if you submit the pre-processing steps, that will make life easier. Simply because your data is so big, you won't be able to upload the data. And so if you do not submit the pre-processing, I can't run your code.
So, in my experience in running like dimensionality reduction takes a long time on those dimensions.
Comment on that in your report so that at least I can examine your code. Okay. Yes.
A lot of my code is kind of like sandbox style and really garbage to actually run or look at. Do you want us to like clean stuff up before we submit, or can we just throw everything into the folder?
Oh man, I should be able to know which number on canvas corresponds to what answer. Submit whatever you want, but at least make it clear how to reproduce your results. That's about, I mean, yeah. I don't want you to submit like 100 gigs of code and say, my answer is somewhere there. I really don't want that. Yes.
So the code for the final project, you should submit it and it should train a single model. And that,
No, I mean, so the idea is that I want your experiments to be reproducible. What that means is every result that you have in your report, I should be able to reconstruct using your code. But given that cross-validation can take forever, I'm willing to let you do the cross-validation and just show me the hyperparameters that are good so that I can run it with those hyperparameters and get the same numbers. This, for example, requires you to set the random seed and such things. Yes.
Not the processing and data, and my experience, for example, in CAS data, some of the ages were in words or numbers and change them. So
You manually change them.
yeah, so how can I?
If you did that, yeah, that's a little bit not great. For the project, it's okay, but in general, you try not to edit the data. You do it in code. You basically create a file that you read both the things and you apply the changes. But since you've already done this, submit that file alone. Yeah. Yes.
You said that you would allow people to just have the final hyperparameters and not do cross-validation.
Yep.
Does that mean you want us to go back to our code and remove the cross-validation?
No, keep it. Keep the cross-validation. It won't be run, but at least it'll be there.
Oh, okay.
Yes.
if I use PyTorch, do I need to like the homework to say to give you the screen?
Yeah. It's very much like the homework.
But do I need to say how to install PyTorch?
I'm hoping that it's already there on CADE.
Oh, okay, has PyTorch.
I don't know, you should check. If not, add a requirements.txt file. Yes,
To clarify, if we did all of our work in notebooks.
Submit the notebook.
Okay, we don't need to put it, to convert it to.
No.
JavaScript.
Submit a notebook, we'll run the notebook. Yeah. Should you, can we include a README file? Please include a README file. In fact, I strongly encourage that you include a README file. One of the worst things in life is to read 150 in implementations of the same code and trying to guess what matches to a number on Kaggle. So please include a README file. Anything you can do to help us understand your code will make our life easier. There are many questions on. So yeah, Kaggle stops accepting submissions by the 27th. So all submissions need to be in by then. And 27th is I don't remember which time zone the 27th is set to be. Make sure that you get that right. You can keep submitting the 6-page report till the 30th, or you have till the 30th to submit the report. There's a question on, can you make a Piazza post on how you want us to post the code for Kaggle so it's clear? We'll probably, one of us will do that. Yeah. For cross-validation, if we don't remember what hyperparameters were selected, do we have to include it in the README? Yes, if you can include that in the README, and that would be helpful. Actually, include that in the report. I want to see that kind of information in your report as well. So include what hyperparameters were selected for each of your runs in the report, and in the README also, if that's helpful. Okay, one more announcement. This is primarily targeted towards the undergrads in the class. I've been told, I know that many of you are seniors and probably want to graduate, but if you're around for another year, the School of Computing is always looking for undergrad TAs, and I was told to advertise this in the class. If you want to know more information, go to ta.cs.u.edu. Okay. So for the last lecture today, I'm going to talk about some practical advice on building applications with machine learning. So I'll be talking about diagnosing problems with your learning algorithm. I'll be talking about how to analyze the errors of your models, and is there like a standard recipe for injecting machine learning into some task that you care about? And I want to wrap up with talking about societal impacts of machine learning and how we should think about this. Really, it's all about making machine learning work in the world from the low level up to its impacts. And some of this is advice that I just put together by observing the mistakes I've made. And some of this is based on readings written and observations by other people. And there are references on the class website. Let's talk about diagnostics. This is something that a lot of you are worried about for your current homework and your project and such things. So suppose you train an SVM or a logistic regression classifier for some task, spam detection or something. And of course, you're doing all the right things. You're doing cross-validation, you're finding the right hyperparameters the right way, which, by the way, turns out is a little bit of a problem for the SVM in your homework. Your hyperparameters that we gave you were not the best. And I think there was a mention about that in PRSA. Let's say you do all of this, and then you find that your classifier is 75% accurate. Maybe 75% is not good enough. Maybe 75% doesn't help the domain where this classifier is going to get instantiated. So the question is, what can you do to improve it? Of course, one obvious thing to look for is bugs in the code. So, I mean, assuming there are no bugs in the code, we all write bug-free code, right? So let's assume there are no bugs in the code. What can you do to make your model better? Any ideas? Yes.
Ensemble.
Ensemble it, okay. That's always a good idea, but at the cost of more compute. Any other ideas? Remember, you're not in the class. I have given you a data set and said, go do the ML thing. But imagine that you're applying this to some task where you control the entire pipeline. Yes.
Make sure that the data that you're training on is IID.
Make sure that the data is IID, so clean up the data in some sense. There's a suggestion on Zoom, feature transformations. You can think of that. So at some point, I try to think of some ways in which you can do this. One of the most important answers there is get more data. It's often the case that adding more training data leads to more better performance. Then you can play with the features. You can add more features, or you can add less features, or you can add different features, or you can change your features. All of these are the right answers, so it doesn't seem to be particularly helpful. Or maybe you want to change your training. Maybe you want to run your optimizer longer. Maybe you want to change the learning algorithm. Maybe you want to change the model or the hypothesis space. Maybe you want to play with regularization so that it doesn't overfit or underfit or something. The problem is, each of these things is expensive. Every one of these things takes time and requires us to think hard about what's going on. This is it's a tedious process. There is clearly a dependence on luck, because some things that you may, some things that you may try might prevent you from trying other things, or something you might not think of something. So for the next maybe 5 or 10 minutes, I want to talk about how you might be a little bit more methodical about this process. The thing is, you can't fix problems until you know where the problems are. So the first thing to think about is diagnosis. How do you know where the problem is? What is causing the problem? It's possible that your model is overfitting the data, the training data. It's possible that your model is underfitting the training data. It's possible that your learning has not yet converged. Or maybe you're measuring something incorrect. Maybe it's working, you're not measuring the right thing. or maybe you're measuring the wrong thing during cross-validation, and so you're choosing suboptimal hyperparameters. All of these things could happen. So let's go over some of these ideas. First, I want to talk about the first two things, overfitting and underfitting. Overfitting is when the training accuracy is much, much higher than the performance on future examples. Performance on future examples is approximated or estimated by the test data. This means that the model has remembered the training data a little too well, and so it's not generalized. Another way to describe this is to use the word variance. High variance is said to be the case where your best classifier, your learning algorithm is said to have high variance, or your model family has high variance if your best classifier depends a little too much on the specific choice of the training data that you have. Had you changed the training data slightly, you might have got a very different classifier. The only reason that can happen is because it's remembering the training data too well. So variance is another word that shows up in this context a lot. And think variance occurs because of overfitting. Another possibility is underfitting. We didn't talk too much about underfitting, but the idea is that there is a certain concept that you are trying to approximate using a model. But the concept is much more complicated, much more complex than the hypothesis space that you consider. So no function in the set of functions that you are entertaining or your learner is entertaining is good enough. If that happens, that means both the training accuracy and the test accuracy are going to be unacceptably low because the model cannot represent the concept well enough. And if this, another word that's used in the literature or in a lot of machine learning context for this is bias. The word bias, unfortunately, is overloaded in AI and machine learning. I can think of at least 3 different meanings of that. And I think today, in this class, in this lecture, I'll talk about 2 different versions of the word bias. Bias, we've already seen the other one, bias term in the linear classifier, but let's not go there. In this case, the bias is the best, take the best classifier that you can get. I mean, not just the best classifier that your learner can get, but imagine an Oracle function that explores the entire hypothesis space and finds the best function by enumerating all of them exhaustively. It's like objectively the best classifier. Bias is the true error of that classifier, is the generalization error of that classifier or that model. And if the bias is high, that means even the best classifier in the set of functions you're entertaining is not good enough. That's underfitting. Any questions? I see there's a lot of discussion on. Okay. Any questions? Yep.
How to calculate bias?
You can't calculate bias because it's the true error of the best predictor. It assumes that you can learn the best predictor and compute the true error. Of course, you can estimate. Both of these, for certain classes of functions, you can calculate them concretely, but in practice, in general, it's not. But you can think of the error of a classifier as coming from both the bias and the variance, plus natural noise that occurs in data. The bias causes the model to underfit, the variance causes the model to overfit, and the error can happen because of both of these things. And this equation, bias equals error, error equals bias plus variance plus noise, is actually an equation for certain specific closed classes of functions. When the bias is high, the classifier cannot represent the data, and both train and test error can be high. The variance is high means that the training error is low, so it makes it look like you have a good model, but the test error can be really high. So high bias is like underfitting, low bias is overfitting. Bias variance trade-off has been extensively studied in the statistics literature, especially in the context of regression, and it tends to be a trade-off. If you're giving up bias, that means you're making your models more expressive. And if you're making your models more expressive, you might end up increasing variance. If you're trying to reduce variance by making your models less expressive, you might end up increasing the bias because you have removed good functions from your hypothesis space. So there could be a trade-off between bias and variance. There's a question? Yes. You mean the hyperparameters?
Yeah.
Not quite. One way or another, it ends up being something like grid search. You try each combination and hope it works and find the best one. The problem is that when you start making, you can, for instance, you can think of that also as a learning problem. But then you'll have other hyperparameters for that other learning problem. So eventually you'll, there is no freebie here. Yes.
Well, if you have like similar data sets, will the hyperparameters, will the best one be pretty consistent? Say, for example, you're running like SVM on backwards, will the same hyperparameter that was best for that one be also the best for like logistic regression?
Not necessarily, because these are different functions.
So use like TF, IDF instead of that, for the same like algorithm.
But then you're changing the data, you're changing the features, and so you're changing the geometry of the space. So honestly, there is no obvious right answer. There are heuristics, there are sort of this folk wisdom, and that's about as much as there is. I'll give you a concrete example of folk wisdom. For training for fine tuning, for a certain type of training, for a certain family of large language models, the learning rate hyperparameter, the recommendation is you pick values between 10 power minus 4 to 10 power minus 6, because on hundreds of data sets, this is the range that seems to be the best. How do we know that? Because somebody tried all of it, right? So there's no sort of scientifically correct answer or mathematically correct answer one way or another. The only, to kind of extend that question that you had, you said if your data sets are similar. If your data sets are exceedingly similar, then maybe what you said might work. But then there is no clear guideline on what exceedingly similar is. So that's where we are. Yes.
Sorry, on that Hopf equation, is that training error, test error, or just more a general concept?
It's a test error.
That's it.
Yeah, because bias involves test error. But that equation is not really a real equation for almost anything except for, I think, linear regression and such things. So this is more about the general concept. But whenever I say error, I mean generalization. But we do know some ideas for managing bias and variance. Ensembles tend to reduce variance because multiple classifiers are combined, and each of these classifiers are typically trained on different sets of the data, different partitions of the data, and by averaging things, you're reducing variance. In general, averaging reduces variance. If you have decision trees of a certain depth, increasing the depth can decrease the bias. Why? Because increasing the depth makes the model more expressive. It can, makes the model more expressive, so it can capture more complex things. On the other hand, increasing the depth can also increase the variance because you might end up overfitting the training data. With support vector machines, we didn't talk about kernels at all, but think of kernels as like an automatic way of doing feature transformations in a sort of a efficient way. When you introduce feature transformations with larger, higher degree polynomials, you're making your models more expressive. By making them more expressive, you're decreasing the bias. But by making them more expressive, you're also increasing the variance. You can also control the bias variance trade-off by playing with regularization. If you regularize more, you are increasing the bias because you're making the models by choosing a hyperparameter that makes the regularizer more important, you are allowing the models to express less set of concepts. So you are increasing the bias, but you're decreasing the variance. There's a question on Zoom that's kind of funny. I heard that some research groups have magical hyperparameters that somehow they just perform better. Is that true? Do we know why? The answer is they tried everything, and as a group, they have come up with these sort of rules of thumb that say that this works, but they don't share everything. So we just know what works. There's a little bit of a reporting bias there. With neural networks, making larger neural networks increases the variance but decreases the bias. Yes.
For something like our algorithm on our onlookers, we are doing SVM on decision trees.
Uh-huh.
Do we expect though the facts to kind of cancel each other out?
Sometimes they do cancel each other out. So when you're doing SVM over decision tree, what you're doing is an ensemble. So the ensemble reduces the variance. However, you're increasing the expressiveness of the combined system. And because you're increasing the expressiveness, you might end up increasing the variance. So it's not sometimes it's not very obvious. And you could have either one of these depending on other factors like your data, the task, the true function, and how the choice of hyperparameters is fixed. We did not cover k-nearest neighbors, but k-nearest neighbors are perhaps the easiest machine learning algorithm that exists out there. So let me give you a 3-minute summary of nearest neighbors. You have your features, right? You have your data, you have your features. A new test example comes along. For that example, you find which of the features, which in training examples are the nearest according to some distance. Let's say the Euclidean distance. You compute the distance between your test example and every one of your training examples. Find the k nearest ones of them, take their labels, and whichever label is the more common one, that's the answer. So for every test example, you find the k nearest neighbors, aggregate their labels, k nearest neighbors in the training data, aggregate their labels. Yes. You can, sure, yes. I was going to do a lecture on k-nearest neighbors today, but then I decided not to because I did not want to do a full lecture on a new topic on the last day of the semester, especially 2 days before the final exam. But k-nearest neighbors are perhaps the easiest thing you can implement. It's also, if you're not careful about how you implement it, it's going to be one of the slowest things you implement. Because for every test example, you're going to find the k-nearest neighbors among every training example. So it might end up being a little uncomfortably close. There's one hyperparameter for k-nearest neighbors, it's k. How many nearest neighbors are you using? If k equals the size of the training data, then you compute all the distances and then take as many examples as there are in the training data. Basically, you just take the entire training data and report the average name. Yes.
This takes the average of the nearest neighbors, right?
It could be some aggregation, average for regression, majority vote for classification.
Is there any reason why we don't use like a distribution over the k?
You could. There are like k-nearest neighbors is such an easy idea that it has been invented many times. What you just said is a variant. You can weight the distances. You can weight the labels by how far they are. That exists. Yes. Okay, but anyway, k-nearest neighbors, increasing k tends to increase the bias but reduce the variance. How do you detect? Yes.
Since the first class of other lessons that other steps of the calculation, is there a specific method that you can choose the first classifier? And especially
Not really. There isn't yeah, so I don't know about the final, but there is no such thing in there is no such requirement for the theory to work. Which is kind of amazing, right? I mean, your choice of the first, there is a sequence of things, and of course, your final predictor depends on how your sequence works. But it's the functional form is going to change, but the training error still keeps going down. So how do you detect high variance? What you do is to plot these sorts of learning curves. The horizontal axis here is how many training examples you have, and the vertical axis is the error. And this curve here is showing the training error. So the training error, as the training data increases, there is some sort of a initial phase where the training error goes up because you have very little data. And so your model is of course going to fit everything. And eventually it will settle into something that's at that level. But then on the same plot, if you plot the generalization error, what you will find is the generalization error also, it goes down as you see more data, but it never, these two curves never really touch each other. They don't get to the same place. There's always a large gap between the training error and the test error. And you see this sort of behavior for larger and more complex models. And this is a telltale sign that the variance is high. You can use exactly the same plot to detect high bias. If you have high bias, that means they may be converging, both the training and the generalization error might be converging, but both of these are converging to a very high level, value. And that means that the best classifier in this data is more likely than not good enough to represent this concept. Yes.
About last slide. Yes. So these two slides means the converged value is large or higher.
The gap between the training and the generalization.
You said it's impossible for them to cross each other.
Why would they cross each other? I mean, it's going to be unlikely that the generalization error will be lower than the training error because your model actually has access to the training data. It's almost, if I see that, I almost think there's a bug. Because your model has access to the training data, it's remarkably unlikely that the error on unseen examples is less than the error on seen examples. At best, you can hope that they converge. Other questions? So let's go back to that list that I had. We had how do you improve the model? You can try to think about what could go wrong. So if you add more training data, that can help with overfitting. Because as the amount of training data gets more and more, it becomes harder and harder for a model of a limited capacity to overfit that data, so it has to generalize. If you use more features, it can help with underfitting. Why? Because your features are not representative enough of the task, and you're adding more features, you're adding to the capacity. And by capacity, I mean something like VC dimension. If you remove features, you can help with overfitting because adding more features can allow the model to better explain the training data in preference to future examples. So removing bad features might help. And then the third thing, use other features. It can help with overfitting, it can help with underfitting because you could do anything in that bullet point. If you play with your regularization, then it could help with both overfitting or underfitting. And depending on your regularization hyperparameter. The last bullet point there on the screen is about hyperparameter selection. So we covered detecting overfitting, detecting underfitting, and one of the better ways of doing that is to plot those curves. Let's take a look at this problem of convergence. Many learning algorithms, if not most, are framed as optimization problems. And something that you should get into the habit of doing as a default is to track the objective function as the objective value as a function of the number of iterations. The horizontal axis here says iterations. It could mean number of epochs. It could mean number of updates to the model. It could mean some, it doesn't have to be you compute the objective at every update, maybe every 1,000 updates or something like that. One way or another, you're trying to minimize a certain function. And when you're minimizing a function, your optimizer is trying to minimize a function. And if it's minimizing the function, you want, as the optimizer proceeds, you want that value to keep going down. Seems like a reasonable thing to do. the question is, when does it stop? So if you stop your learning somewhere here, then clearly the objective has a while to go before convergence. But in this region, maybe it's still going down a bit, but it really does not matter if you stop at the beginning of that. Because the incremental gain that you get beyond for running for another bunch of iterations is not too much. So you can stop, you can choose a model from right here. How do you know how do you do this? Well, you run your training for longer than necessary, and then retroactively pick the models that has this sort of convergence property. This is not easy to decide, because imagine that the loss curve looks something like this, or the objective curve looks something like this. It's clear that it's not converged here, but what about there? Maybe it has, maybe it's not, and it's not necessarily clear. And once again, we are back to this sort of guesstimating that we're doing. Yeah, it looks like it's converged, let me stop there. And this does happen quite a bit. And you're doing in your homework 6, several of you have commented that this is a bit of a pain. You don't know how many iterations to run. And the answer is we don't either. We need to, it might depend on the data set, it might depend on the model, it might depend on the objective, it might depend on the problem. We need to just plot these curves and figure out what a good stopping criterion is. And in the previous lecture, we discussed stopping criteria. Yes.
In homework 6, you mentioned using like a relative difference
Yes.
with the objective values.
Uh-huh.
Wouldn't that cause you to like stop iterating too early?
It
Not
could.
converge?
For instance, it might, this relative difference between here and here might be too high, and you might say, yeah, that's a big jump, so let me now keep track of this, and it may look like this area is much smaller, so you could, yeah, the jump is much smaller, so you might decide to stop. That's possible. I think one of the better ways of deciding convergence is, in addition to plotting this plot, in addition to plotting the objective, you also plot accuracy or error or some sort of performance metric on held out data, on data that was not available to the learner. And at that point, you don't plot the loss, but you plot the accuracy. Remember that loss is just a differentiable substitute for the true metric that you care about. So you plot that metric, and typically what you might find that that metric might go down and then go up a bit. And so that gives you this sort of a good stopping criterion where on this side you are overfitting and it's not good enough. Yes.
Why don't we default to using our metrics instead of the actual loss?
You could, I'll tell you why we need to also plot the loss. Because all of this is fine, but if our loss does something like this, we know there's a problem. So plotting the loss is almost like a sanity check. We are minimizing a function, we expect the loss to go down. And if that doesn't happen, there's some problem. It's almost like a unit test. And it's good to get into the habit of plotting the loss function always, just for this, just to avoid this. And for the most part, if you're using well-studied, well-used code, this will not happen. But every now and then you might find that maybe you have a bug in your code. And this is like a debugging. For a stopping criterion, I would suggest using the held out data. And that tends to be a better way of estimating. Yes.
Just to ask, if we were to use the test data as the stopping criterion.
Don't use test data. Use held out data, validation data.
Okay, so that data
Yes.
for this accuracy and using that to decide when to stop. But actually, I guess you could have answered the question. just
Okay.
with that phrase.
Okay. Yeah, I figured that yes. So, we are, if you're doing gradient descent on a convex function or stochastic gradient descent, we expect the function value to go down. However, there are a few caveats here. With stochastic gradient descent, there is randomness in the process, which means you may not see a smooth curve of this kind. What you're more likely to see is some sort of a wiggly curve that the wiggles just kind of decrease as learning proceeds. So there might be locally the loss function might go up and down because you're choosing random examples to make updates. So that could happen, but the general trend tends to be down. The other caveat is with respect to stopping conditions, with respect to starting points. With neural networks, initialization matters. So different initializations can lead to different kinds of different loss functions, and that tends to add to the complexity of this process. So going back to this thing, if you want to make sure that your training has converged, you need to track the objective, you need to track the generalization or the handout set metric to make sure that something weird is not happening there. Any questions? What we just talked about is to address this question of, does your learning converge? The final point that I want to talk about with respect to diagnostics, which often we don't get this wrong all the time, but sometimes we get it wrong just because we're not thinking about the problem. So it's worth just always thinking about, are we measuring the right thing? For classification, often the default measurement tends to be accuracy. For regression, the default measurement tends to be something like mean square error. But as you're seeing in your homework, if your data set is not balanced, then accuracy can be highly misleading. So if you have 1,000 positive examples and 1 negative example, any classifier that predicts always positive will have 99.9% accuracy. But of course, that's not a good classifier. So if your labels are not balanced, then you might have to use precision recall and F-score as you're doing in your homework. But there are other metrics that exist. There are other metrics that might come from the specific application that you're looking at. For instance, maybe imagine that you're building an image classifier. The image classifier might need to kind of put boxes around pictures of cats. So there's a photograph, it needs to put a box around all the pixels that contain a cat. There, a common metric that might be used is what fraction of the true cat pixels did your classifier get inside the box. It comes from the application. Often the metrics and the measure of success comes from the application, and it's worth knowing about how your model will be used in deciding what that metric would be. Yes.
Precision and recall and F-score. These metrics are not symmetric across.
The labels. Yes.
So do we select the label that is that has smaller proportion in the data or not?
So let me repeat the question. Precision recall and F-score are not symmetric across labels. Precision is defined for a label, recall is defined for a label. So the question is, which label do we pick? And often the answer there depends on which label you care about more. I'll give you a concrete example. Let's say that I'm building a classifier that looks at chest X-rays to decide whether there's some illness or not. I can define positive means there is the illness, negative means there is no illness. And I would probably measure the precision recall for the positive labels. Why? Because it matters more for the application. But you could measure all, the precision recall for all the labels, because that could be useful, something useful to report. In multi-class classification, typically you measure precision recall for all labels separately, because you can't, typically when you have only 2 labels, this choice doesn't matter too much, because if precision increases for one, then the recall decreases for the other and so on. So they kind of balance each other. So it does not, the choice of the label does not matter too much. With multi-class, it does. And so the standard thing is you report precision recall and F-score for every label. And that's what you do. Other questions? Now let's talk about error analysis. In the context of this class, actually, I want to talk briefly about how much of machine learning is engineering before I talk about error analysis. So, you've been setting up your machine learning experiments, applied machine learning, we've seen a lot of math. We've seen things like theorems and ways to kind of the connection from math to algorithms and so on. But applied machine learning is entirely an empirical science, which means we need to follow good experimental practice. There is a lot of work in what it means to run good experiments, a lot of literature on that, and of course, I'm not going to do justice to any of that in the next few minutes. If you're interested, you might be able to find material on that. The people who actually excel in this are people not in computer science, but people who work in the sciences, because the experimental procedure matters a lot more there. For machine learning, you need to have something that trains a model. A learner takes a data set and some choice of hyperparameters to produce a model. And each learning algorithm will have its own hyperparameters, and the learning algorithm knows its own hypothesis space. So I can write learning as this one function that called train, that takes labeled examples and hyperparameters and produces a model. Prediction is also a function. Prediction takes an example and a model and produces a label. And different models have their own versions of how prediction works. Linear classifiers take a dot product and threshold. Decision trees do the whole thing where you walk through the tree. Neural networks use a forward pass. Ensembles call all the low-level models and then aggregate the labels. One way or another, every hypothesis space contains its own prediction function. Every model knows how to make a prediction. And then there's the evaluation. Evaluation it uses a test set, it uses a collection of labeled examples and a model, and it produces a collection of metrics. Metrics could be accuracy, precision, recall, and all those things. So evaluation is also a function. I'm basically describing the sets of functions that you might have to implement, no matter what your learning algorithm does. And we talked about the evaluation metrics. And there's hyperparameter selection. I'm calling this more generally, you see the phrase model selection. What model selection does is it takes a collection of labeled examples, a learning algorithm, which internally could instantiate that train function that I had, a collection of possible choices of hyperparameters, and it produces one collection of hyperparameters that it thinks is the best. One example of model selection that you've been looking at in the semester is cross-validation. Cross-validation does exactly that. It takes a training set, it takes a learning algorithm, takes a collection of hyperparameters, and then it says this collection of hyperparameters is the best. But you could do other things. You could use a held out set. Because cross-validation could be expensive, you just train on a partition of the data, always evaluate on the held out set, and then use the held out set to rank. Doing that is equivalent to doing just one fold of the k-fold cross-validation. So you don't get the averaging across the folds. And sometimes that's all we can do because that's how much time we have. So if you put that all together, you have a function called train, you have a function called predict, you have a function called evaluate, and you have something that does model selection. And then let's look at the life cycle of how the learner might operate. You have some training data, and you have some choices of hyperparameters. And at this point, you might want to think about everything that I'm talking about here. You might want to think about how this has worked out in your homeworks or in your project. From the training data, you might construct your cross-validation splits. You still have your hyperparameter choices. Together, the cross-validation splits and the hyperparameter choices can be used as the input to cross-validation, and you get the best hyperparameters. The best hyperparameters on the entire training data, when applied to the learner, gives you the model. The model, when applied to the test data, in conjunction with the test data, when given to evaluate, gives you some metrics. And then finally, the model gets deployed. That's the model. So there's like a complicated sequence of things that you need to do before you have a model that you can sell. Sometimes you might not have the time to do cross-validation. You just use a validation set, which is just one split of the cross-validation, and you just get the best hyperparameters on that validation set. Why? Because cross-validation is computationally intensive. This is all you have the compute budget for. some people here might prefer a functional way of thinking about this. A model is something that takes an example to a label. A learner is something that takes the label data and hyperparameters to a model. Evaluate takes label data and a model and gives you a metric. A prediction takes a model and a future example or an unlabeled example and gives you a label. Cross-validation takes a learner, which is basically of the type trained, and a hyperparameter set and gives you the best hyperparameters. There is some, when you're doing your experiments, you need to make sure that your train, validation, and test splits don't have any overlaps. Because otherwise, your training examples, if they show up in the test set, then your test set is no longer a good representative of the generalization, the model's ability to generalize. If your training examples contaminate the validation set, then your validation set is no longer a good representative for future examples, which means you may not be able to get good hyperparameters. So make sure that there is no contamination. And this is actually a big problem. This is a big problem, especially when there might be societal pressures that we need to find a model that gets accuracy on this benchmark. We have to get the best accuracy on this benchmark. Let me just train on this benchmark. And that way I get the best accuracy on the benchmark and I'm done. So there might be that, and sometimes it might be really hard to disentangle the data. Right? It might come with, it might actually be problematic for the domain where to disentangle because you might not be able to get IID splits. Some data sets come with standard splits like you see in your homeworks and the project. But the bigger point I want to make here is think about the amount of infrastructure that needs to be in place. There is so much infrastructure involving reading data sets, playing with them, partitioning them and all that. You need infrastructure for logging, you need infrastructure for checkpointing, saving models just so that if your program crashes, you can recover. You might need one sort of a sanity check that you always need to have anytime you implement a learning algorithm is you need to test on toy data sets. Always test on toy data sets whose properties you can control, because then you know whether your learning algorithm works in the best case scenario or not. Any data set that you find in the wild is going to have noise in it. It's going to have unknowns. For example, you can any SVM or logistic regression implementation that you have, you should test it on toy data sets with 2 dimensions where that is linearly separate. So that way you know that your SVM is going to perform well. There's a lot of infrastructure that goes into building the machine learning part of this pipeline. And part of what you're doing in this class, in the homeworks, is actually building some of this infrastructure. A lot of these things might seem familiar. Maybe you're not doing checkpointing and logging because by any measure, the amount of time that your homework and project learners take is actually pretty small. We're talking about the learning algorithm running for months to produce one classifier. So you don't want, after 15 days of non-stop running, you don't want to have discovered a bug. Or you don't want someone accidentally tripping over the wire and pulling the plug, and you have to restart your learning. So you want to, there's a lot of infrastructure. But that's really not what I want to talk about. In this class, your machine learning code has taken the center stage. Like all the code that you write, one way or another, connects to the machine learning part of things. But in an application, that same box is really a tiny part of the whole thing. There's a whole other infrastructure that we've not talked about. This is ML ops, machine learning operations. You need to set up configurations that manage your hyperparameters. You need to set or the entire systems. You need to have data collection pipelines. You need to have feature extraction pipelines. You need to have serving infrastructure. You need to have monitoring infrastructure that monitors the serving infrastructure. Like an incredible amount of software engineering goes into keeping machine learning systems running in anything but the most trivial cases. For me, for example, concretely, people talk about ChatGPT as being an amazing example of AI. One of the most incredible things about ChatGPT, as far as I'm concerned, is the amount of engineering that has gone into it to make it look seamless. This is a product that's millions of people started using in a span of a few weeks. And for the most part, it did not crash. If you want to ask me what better motivation is there to learn software engineering in the age of ChatGPT, the answer is so that you can build ChatGPT. All of these other things around these sorts of infrastructures are extremely robust, and they have to be in order to maintain the performance. Machine learning systems can get really heavy. Machine learning code, and both the internal and the outside, can get really hairy, really complicated. And if you're not careful about designing these systems carefully, using the right software engineering practices, then you might be accruing what's sometimes called the technical debt. Because you might be quickly building something and making it work. A month down the line, your future self will hate you because you used a variable I to mean an integer here and I to mean a string somewhere else, and you never bothered to change this. All of you have seen bad code, right? Some of us sometimes even write bad code. But imagine that bad code is now out there deciding whether someone's chest X-ray has a cancer or not. It's kind of scary when you think of it that way. So machine learning there's a lot of really amazing math and algorithms that go into machine learning, but there's also a system building part of it. And ML ops is really an important thing. Going away from infrastructure, I want to talk briefly about error analysis. Machine learning typically plays a small role in a larger system. There is usually existing infrastructure out there, and you want to change one piece out and bring in some sort of a learned component. But in deploying this, we need to know about what assumptions we made while gathering the data, and what assumptions we made while pre-processing. We need to understand how the features affect the domain, are relevant for the domain, any data transformations, like feature transformations that we may have had. User interface becomes a big deal. And sometimes each of these pieces can contribute to the perceived error of the machine learning system. So error analysis is really the art of ascribing blame to the different parts of the system for perceived error. Let me give you a simple example. This is a somewhat dated example because this is not how text processing pipelines work today. But imagine that you have some text. You can break it into words. And maybe you want to find the parts of speech in the words, and it depends on the full text and the word. Maybe you want to find the parse trees for these things, and it depends on everything that came before. And then you use all of these things as features into some ML-based system that predicts, I don't know, whether this movie review is positive or not. This is a dated system. This is not how we do things in NLP these days, but it's a good example for a complicated pipeline where every step depends on a bunch of the steps that came before. Each of these underlying steps themselves could be from a machine learning system, so they themselves have error. So one of the questions that error analysis asks is, how much do the various steps in the pipeline that came before the ML system contribute to the error of the ML system? And one way of doing that is to replace the predictions in the pipeline with the ground truth and ask how much does the accuracy increase when we replace a certain component with the ground truth. So for instance, if I have a full end-to-end prediction of a system that gets 55% accuracy, when I toss in the ground truth words, the accuracy increases to 60, and when I toss in the ground truth parts of speech, it goes up to 84. It looks like the biggest jump comes from increasing the parts of speech, and so the biggest contributor to the error might be the part of speech system. This sort of analysis could be helpful in deciding how to make the system work better in the next iteration. This sometimes this sort of a thing could also be done with something called an ablation. You try to explain the difference between the performance of a strong model and a weaker model. And you may have, imagine that you have a data set with 100 features. and you want to ablate the system by removing 50 of them and asking how much does the performance drop? And if it drops a lot, that means the 50 features that you removed are important. This sort of the general idea that I'm kind of pushing for here is it's not enough that you have a classifier or a model that's accurate, that's good according to some metric. It's also important that you understand why it works, because if you don't, it's possible that you might have accidentally overfit even on the test set because of ways in which you might have collected your data. There might be biases in your data, and you might have the accuracy numbers that you're getting are actually high, but for the wrong reasons. And you want to discover those things. Machine learning systems don't get used in isolation. Let me give you an example to illustrate that. Here's a picture of a so-called machine learning protest that took place outside CMU, where people are holding placards about support vector machines and Bayesians against discrimination. But that's not really the point I want to make. How many people do you count in this picture?
2.
Wait, how can there be 5, 2, and 6 people? Like,
Father.
Well, I see someone's hair bun.
okay, so good.
So
let's see. There's a hair bun, head, neck, person, hand, right? But instead, let's say that we have a classifier. We have a head detector, we have a hand detector, and a leg detector. There are 3 heads, 3 hands, and 4 legs. At best, about 2.5 people, right? So this is the thing. Machine learning systems don't get used in isolation. There are 5 people here, but we only see 3, like parts of people. And we know how the world works, and we are able to put these pieces together to come up with a consensus answer that's really none of these things. Learned systems are not used in isolation, but used in conjunction with larger software systems and in conjunction with each other. So the context of the application matters in making any sort of decisions involving a learned system. Let me talk about injecting machine learning into some tasks that you care about. Or maybe let's talk about injecting machine learning into a task that maybe nobody cares about. Let's say that we want to build a classifier that predicts whether a certain fish is salmon or tuna. Why would you want to do this? I don't know. But how would you do this? At a high level, I can think of 2 different strategies for going about this. One of them might be to think about carefully identifying the best features, carefully crafting the data set, thinking about all the software architecture, designing the learning algorithm if necessary, and then getting all the infrastructure set up, then executing it because you thought so hard about it, you run it once, you get it right. This kind of a strategy can lead to new learning algorithms. It leads to research type things where you are able to think hard about it. Alternatively, you could first implement something, see where it fails, and then keep iterating till it gets better and better. This leads to faster solutions. This can lead to products that you can actually put out in front of people. And neither of these are the right answer. Neither of these are the wrong answer. You might want to not optimize everything upfront prematurely. At the same time, you don't want to commit to a wrong path. So you have to think hard about this. And I've noticed that at least in applied machine learning, people tend to kind of gravitate towards the extremes here, when in fact the right answer is to keep iterating across both of these things. But you do need to watch out for certain things. You need to know whether you have the right evaluation metric. You need to be careful, almost paranoid of contamination of your training data, because learning is all about generalizing to new examples. When I run machine learning experiments, I try to make sure that I don't even look at the test examples, because I don't want to contaminate my model by accidentally having looked at the test examples, and through my brain, I choose some hyperparameters that accidentally overfit the test set. So I end up suggesting that you compress your test data, put it in a zip file, don't even write code to read that data until at the very end, you're ready to actually deploy a model. A common cause for error might be that one of the features in your data is actually the label, in which case you'll get 100% training accuracy, and that's about it. Any classifier that gets 100% training accuracy, you should be extremely suspicious of, because real life is not that kind. That sounds so pessimistic. Be aware of the bias variance trade-off, or the trade-off between underfitting and overfitting. Be aware that sometimes intuitions just don't work in high dimensions. You need to actually prove things because of something called the curse of dimensionality. Sometimes there's a lot of beautiful theory in machine learning, but sometimes the theory might just be that. It may not actually transfer to practice. Because it might make invalid assumptions. For example, the perceptron mistake proof, the mistake bound, assumes your data is linearly separable, and says, if your data is linearly separable, then the perceptron algorithm will find the best separator. Okay, most concepts in real life are not linearly separable. What then? Or you could have proofs that are only real in the limit to infinity. Stochastic gradient descent will converge to the true optimum of a convex function if you run it forever. I'm not going to wait forever. It turns out that for stochastic gradient descent, there are also bounds on how well you can converge, but you need to find those kinds of bounds. But nothing is going to beat experiments on real data. Proving something is great, but getting experiments to work is also important. We keep hearing about big data. Actually, we hear a little less about big data these days, and we hear more about AI, but that's just how the press works. But more data is always better, but cleaner data is perhaps more important. But it's not just enough to toss in all the data that you can find. Learning is impossible if you do not have some sort of assumptions that are simplifying the hypothesis space or guiding your learner search through the hypothesis space. Because otherwise you might end up aggressively overfitting the data. Learning requires knowledge. If there's one lesson that I want you to take from the semester, it is that machine learning is not a magic wand. It's not going to just magic. You can't sprinkle machine learning on a problem and make things better. You might actually make things worse. Knowledge becomes very important. Knowledge can take different forms. It could help you decide which model or which model family is better suited for the stars. Maybe linear models are better suited for certain kinds of things. If you have categorical features, maybe you want to try this decision trees. Maybe you have features where the inputs are raw sensor data or raw data, and you can't think of any feature transformations. Let's use a big neural network. You have a sequence of, each example consists of a sequence of things. You want a neural network that's better suited for sequences, and so on. Another question is, what learning algorithm? Maybe your learning algorithm makes certain assumptions about the data, and those assumptions are invalid. Maybe you need to choose a different learning algorithm. Maybe your learning algorithm requires gradients of the loss function, but your hypothesis space does not always admit gradients. Sometimes this choice actually does not matter. One thing that often does matter is the choice of the right features. If you have the right features, learning becomes easy. All of these are really claims about the nature of the problem. They are claims about what you believe the oracle function is doing. Other random advice, always start off with simpler models. If nothing, at least you'll get some baselines that you can beat later. Someone mentioned ensembles as a good example, good thing to try to make your model better, and that's always good advice. Ensembles seem to work better, but the price you pay is extra computation. And sometimes you have to ask yourself, is machine learning even necessary here? Is machine learning even possible here? I'll give you an example of an application where machine learning will not work. I want to use machine learning to predict something that is truly random. Of course, there's no generalization possible. How can you hope to discover generalization? You find patterns, but no generalization. This takes me to the last part, where I'm going to talk about making machine learning matter out there in the real world. There was a keynote talk at ICML. ICML is short for International Conference on Machine Learning. It's one of the premier venues for machine learning research. There was a keynote in ICML 2012 by Kiri Wagstaff. Kiri did her undergrad here at Utah in the 90s and then has gone on to have a distinguished career in machine learning. Most recently at I think JPL, working for NASA on data that comes from Mars. So she posed a few challenges to the larger machine learning community. It's all nice if we can prove theorems and build models that can do identify cats and images, but can we? She posed challenges to the community. Can we have a law that's passed based on some ML analysis? Can we have $100 million that's saved because of decision making that ML has supported? Can conflicts between nations be averted by translation that is powered by ML? Can we have a 50% reduction in cybersecurity break-ins because of ML-based security? Can we save one human life because of a diagnosis that is machine learning supported? Or can we improve a country's human development index by 10%? It turns out that some of these challenges have already been met. I believe that instead of thinking of $100 million being saved, there are hundreds of millions of dollars being made because of ML systems. For example, Google is a company that relies not exclusively, but heavily on ML. There are a few other things, there are other like human life. There are advances past. This is almost a decade, more than a decade old now. Things have moved past where they were in 2012, but still, I think the answer to some of these things are not conclusively yes. There are some challenges for you all to think about. Data-driven decision-making is increasingly prevalent, and algorithms that we see in the class are not just proof of concept anymore. And this means that algorithmic decision-making is affecting us more directly than it did even, say, 5 years ago. When we talk about classifiers might exhibit certain types of biases. Data sets might exhibit certain types of biases. How do we ensure that these data sets and classifiers explain their behavior in a transparent way? When can you believe your model? And when can you actually overrule the model's prediction? And by the way, from now, the next 5 minutes, everything that I say is going to be framed as a question because I don't know the answer to these things. These are the kinds of challenges that are for all of us to address. What if these statistical models end up provoking certain decisions that are ethically dubious? Importantly, these are not any of the criteria that we have loss functions for. These are not the things that we are optimizing when we train our models, but when we deploy machine learning systems, these things start to matter. Let's dive in a bit. So classifiers can be biased. Imagine that a classifier is used to decide how long someone should be sentenced for crime, or should someone be granted bail, or should someone's application for a job be considered seriously or not, or any of those things where people's lives are at stake. These are all real-life examples. None of these are made up. These actually happen. There have been lawsuits. There have been public embarrassments because of these things. There have been classifiers that have decided whether a resume should be sent up for screening. That screen resumes, for instance. And now, when we do that, when the decisions of these models affect people, a question comes up. How do we know whether these classifiers are acting legally or ethically? And how do we know whether they are not being unfair? Imagine that your resume got rejected by Amazon. I'm just picking Amazon as an example, because an automated system decided that they don't like the spelling of your name or something like that. How do we guarantee that these learned systems don't do harm or don't do harm to specific groups of people? It's a non-trivial question. It's a question that's not just a technical point. It's not just, you can't prove a theorem around it. It involves people. We need algorithms. But at the very least, we need algorithms. We need new ways to think about evaluation that avoids these sorts of biases. Part of the problem, but not the entire okay, in the entirety is our data collection processes itself might be biased. And so how do we audit data collection and data sets for these sorts of biases? Imagine that you have a job, some of you do, and imagine that a machine learning system decides to fire you. And this machine learning system has been certified to be 99.99% accurate. It makes one mistake out of 10,000. Just so happens that you are that mistake. Seems like a fantastic classifier until you are the one who's at the other end. So if this happened, if it was a person that decided to fire you, you have the right to an explanation. Could we design machine learning systems or statistical methods that not just make predictions like we saw in the class the entire semester, but also give explanations for why they made the prediction? Explanation is an act of communication. Communication is something that we are humans, we do naturally, which means now we need models that can actually do more than just make predictions. This is a non-trivial question. It's completely an open area of research, extremely interesting area of research. Part of the problem is that our legal systems are kind of outdated. Maybe it's time to update some laws. Recently, there was a law in Utah that passed on how AI can and cannot be used. And there's some effort around the world on AI regulation. But there's a lot more that needs to be done. And the reason I'm bringing this up in this class is because these laws are going to get written whether we like it or not. And it's important that we have some say in that, because people who know machine learning, and you are part of that, should be able to influence the world that we are going to live in. So for instance, some examples to think about is, imagine that evidence is faked using a generative language model or an ML-based auto self-driving car causes a crash. How do we handle that? All of this falls under the umbrella of something called fairness, accountability, and transparency of algorithms. And these are all difficult questions, but these are all the kinds of questions that we have to, as a group, address. In the next 2 minutes, I want to take a quick retrospective look at what we saw in the semester. In the first lecture, I talked about learning as being equal to generalization. The most important point of learning is generalization. It doesn't matter if your learner can explain the training data. If it does not generalize in the future to future examples, it's not worth it. We saw different types of models. We saw linear classifiers. We saw decision trees. We saw nonlinear classifiers through feature transformations and neural networks. We saw ensembles, which can also be nonlinear. There are different learning protocols that exist. We primarily looked at supervised learning, but if you're interested, you can follow up on things like unsupervised learning and semi-supervised learning as well. We saw different types of learning algorithms. There are online algorithms where the algorithms encounter one example at a time. There are batch algorithms where the algorithms see entire data set and keep iterating through it again and again. Along the way, we did not actually see this, but hopefully this question becomes more, this point becomes easy for you to understand, especially because of the project. The right representation of the features matter, of the data matters. And this calls for feature design, your choice of good features. We saw some theory of machine learning. We looked at the question of how learning is defined mathematically. We saw this in 3 different ways. What does it mean to learn? We looked at the 3 different types of answers to this question in the context of online learning, in the context of PAC learning, or probably approximately correct learning, in the context of Bayesian learning. And each of these define criteria for what it means to learn. There are many, many different things that machine learning is a collection of a large set of ideas. It's just a bunch of phrases, some of which hopefully are familiar, some of which are not. But it's a collection of a large set of ideas. But I'm going to argue that machine learning is a little too easy. And this might be, you might strongly disagree with this point, but actually it turns out that if your code is fine, most algorithms work roughly the same. It doesn't, like, the choices that you're making don't matter so much, which is kind of amazing because there's a whole diverse collection of ideas and they're all converging into something that is fundamentally seems to be correct. We did not cover a lot of things. We did not cover a whole bunch of topics, and I'm not going to read them out. But what we did see is the foundations of how to think about machine learning. There are many classes that if you are interested in following up, you can follow up with data mining, a bunch of AI classes, applications of AI, data visualization, or some specializations like deep learning and such things. Some of these are even being offered in the fall semester, so you can follow up on that. This course was all about the foundations of machine learning, where I'm hoping that we cover some of the underlying concepts and the algorithmic ideas that contribute to this field. They're not about a specific machine learning model or a specific library or any single learning paradigm. We saw a broad theoretical and practical overview of machine learning approaches and algorithms. You hopefully gained the ability to implement machine learning algorithms through your homeworks. And in fact, if you think back at the semester, you've built the beginning of an entire machine learning library. And through practice, hopefully you're kind of getting a sense of where machine learning can be applied and where how to go about this process. I am 2 minutes over time, so I'm not going to keep talking. That's the end of our semester. Thank you so much for a fun semester.